Hi everyone, nice to see you here today on a different schedule, but I think it's for a very, very nice talk that we have today. First of all, I'm Rita, I'm part of XGeeks, and I'm super excited to see you all here today for one more of our live streams. So if this is not your first live stream, nice to see you again. It means the previous ones were good and this one is going to be even better. And if you're new to our channel, it's awesome to know that you're here. And again, I hope this is the first of many, and welcome. Feel free to follow us on our social media and also to subscribe our channel. And if you're watching us afterwards in recording, awesome too. Leave us some questions, leave us some comments. We'll also follow up on that. As a reminder, let's talk about XGeeks very shortly, since this is XGeeks YouTube channel. XGeeks is an engineering company focused on providing capacity to product companies. We're not a typical project company due to several factors, and that could be a talk just by itself, but let's leave it to another day. But mainly because we have a huge focus on community, a strong engineering culture, and a great product drive. XGeeks represents what we believe a great balance between project and product. Our teams across Portugal work in building products while dealing with a broad stack. So if you want to know more about what we do, about XGeeks, our team, open positions, our content, what we've been up to lately, you can make sure to follow us on Twitter, LinkedIn, Instagram, Medium. We do some cool stuff there, at least we think so. So I hope to be able to see you around and to see you again in our live streams. But for today, I wanted to introduce you Connor McDonald. Oracle Database Explorer and enthusiastic is our speaker. So I'll bring Donald to stage and let's go. Hey Connor, it's nice to see you here. Thank you so much for your availability to join us.
No worries. Thanks for thank you very much for inviting me. I must warn you, if you hear helicopters in the background, I literally just got a text from the WA police. There's a global alert out for a missing toddler in my area. So hopefully they'll find the toddler. Well. Hopefully the helicopter sounds won't be too bad, and hopefully my dog won't go nuts from the helicopters.
Let's hope for that. It's fine. I also had a bit of a hiccup in terms of connection, so it's fine. But I think it will be a great talk either way. So as you know, guys, Connor will be our speaker of today. He'll give a talk about slow database equal slow application. So this session will be focused on that topic and how SQL is processed, how to avoid getting hacked, and how to get data back to your application in a snappy fashion. So there will be space for questions. So Connor will also be available to answer to your questions during the presentation, the talk, but also during at the end. So you can feel free to also leave them in the chat. We'll of course go through them. And I think having this said, I just want to thank you again, Connor, for this availability of yours. And let's go through your presentation, right? The stage is yours.
Okay, so if you can share my screen, that would be great. Welcome. Oh, I've already hit the enter key. Welcome, everyone. For those that don't know me, my name's Connor McDonald. Greetings from Perth. I'm coming to you from Perth in Western Australia. It's just gone past 10 p.m. It's generally the usual time I give webinars here in Perth because I'm on the wrong side of the world. But thank you very much to XGeeks for having me. To get in touch with me, there's many ways of doing so. Easiest way for casual tech conversation would be on Twitter. If you like your content more in the longer form, I have a blog at connormcdonald.com. And since you're watching a video right now, you may be interested in video. I also have a YouTube channel. We're just about to coming up to 500 videos now at connormcdonald.oracle.com. Now, before we begin, I will return to that bio slide and let's address the elephant in the room. Yes, I do work for Oracle Corporation, and that sometimes inspires dread in people, especially in development communities, because they sometimes think of Oracle as the big nasty. But I promise you, I'm not from the sales part. I'm not trying to sell you anything. In fact, there's one slide about halfway through our content which has the word advertising on it. So I'll be very upfront there. And even that will be something that is free. So no sales tonight, just talking technology and the database. Now, I'm going to start with a little bit of controversy to start with. So this talk, as I said, is about SQL. And many people, when I do this talk about SQL, ask me a simple question. They say, why? I mean, why would you want to talk about SQL? It's not like some sort of brand new technology that's just recently emerging onto the landscape. And so I thought I'd justify why I'd like to talk about SQL first before we jump into the nuts of the topic. So here's the first reason why. Sounds strange, but SQL isn't really sexy anymore. As I said, it's mature. In fact, to say that it's mature is perhaps a little bit of an understatement. If you ever think back to the very first version of Microsoft Windows, well, SQL came out before that. SQL's been around now for nearly 40 years. It's a very robust but old technology. And the problem, of course, there is that developers don't want old technology nowadays. What developers want is sexy, cool technology. They want things like microservices and stuff like that. So where does SQL fit into that picture? Well, I'd make an argument that maybe SQL is in fact microservices. I went to the Wikipedia page for microservices and saw the definition that said, what is a microservice? It's a fine-grained unit of work to do a single function, but each service is minimal and complete. Well, that's pretty much what a SQL statement is. The SQL statement does one particular function and it's complete. It literally does everything it needs to do with the one command. There's no series of steps. It's a single, simple piece of code that actually does one particular purpose. So I would argue that if you're interested in microservices, then perhaps SQL is one of the very first microservices that ever existed. And of course, microservices is almost 2020 nowadays. Now we're moving into 2021 or 2022. Nowadays, it's all about API-based programming, functional programming. So maybe SQL is also one of these modern technologies as well, like APIs. I looked up the Wikipedia entry for APIs. And I saw we abstract the underlying implementation and we describe the expected behavior, but we don't actually describe the implementation because the implementation could be done in many, many ways. But that's also exactly what SQL does. Here's a slightly more complicated SQL, which does a join between two tables, the people and the address table. It does one particular purpose, but the implementation is actually abstracted. We don't actually know how the database technology will implement this function. And even from our own sort of casual perspective, we don't know whether the database will, for example, start with the people table first and evaluate the age criteria first, or maybe it'll start with the address table first and evaluate those predicates first. We don't know. And in fact, the database could do either, depending on which it thinks is the best option. That is quintessentially the definition of an API. We don't know the implementation. We simply have the exposed interface to the outside world, and the implementation is hidden. So if you're interested in all the sexy technologies out there, like microservices, API programming, etc., I'd argue that SQL fits right into that perspective, even though it's 40 years old. Second reason why I like to talk about SQL is SQL sort of got a bad name the last few years because everyone started talking about NoSQL. But it's funny how the NoSQL name has sort of drifted into unpopularity nowadays. And now everyone's talking about new SQL, which essentially is people have realized that NoSQL is actually not the most trivial thing to do as an implementation if you're a developer. And in fact, these are some quotes I've dragged out from Google. The complexity of dealing with a non-ACID-based store, or Facebook. They started in the Hadoop/Cassandra world, and now they're bringing in relational. These two giants of data, probably the biggest data stores on the planet, have realized that even with those huge challenges, maybe going back to some of the relational SQL-based technologies is the way to go. And in fact, I dragged this off an Uber blog post, literally, I think, posted this week. And they're once again moving away from NoSQL to what we call the new SQL environments, i.e. SQL-based language interfaces to cloud-native platforms. And they even said, we originally traded consistency to have high availability. That made it really, really hard. And that's from Uber. And the final reason I think it's good to talk about SQL is probably the most controversial reason, and that is there's a problem at the moment in the IT world when it comes to database, or in fact, application performance. And that problem is us. And let me explain what I mean by the problem being us. A little bit of a small digression here and a history on database servers. I've been involved in IT for about 30 years now. And so I've seen the evolution of servers as we go. Not too long ago, this is what all servers look like. When I went to college or university, this is how we learned what a computer looked like. They all talk through this thing. You can see on the screen there a multi-load FSB. And FSB stood for front side bus. And what the front side bus was, a computing architecture that meant whenever you wanted to talk between two things, a CPU and memory, CPU and IO subsystem, it all went through the bus. And so what that meant was is as CPUs got faster and faster and faster, we didn't really see any benefit because everything was capped at how fast things could travel along the front side bus. This was a beautiful time for us as developers because servers literally couldn't run fast enough. And the great thing was, it didn't matter what code you wrote, you could always blame the server. If your systems weren't fast, you'd say, well, unfortunately, server architectures can't just do what we need. And then AMD came along and ruined it for us. They absolutely destroyed this for us because they invented this thing called hypertransport. When I say invented, the rumor has it they borrowed it from Silicon Graphics, but either way, hypertransport was the first architectures where we bolted CPUs directly to memory. And you had this effectively the NUMA style architectures where now the CPUs could actually run much, much faster because they were directly talking to memory and not going through a bus. That memory access direct from CPU totally transformed the server landscape. And in fact, even inside Oracle and SQL Server, all the benchmarks were done on Opteron-based computers because they were the first servers that really started using hypertransport. Intel saw this, didn't want to miss out. Around about 2007, they introduced this thing called the Quick Path Interconnect Architecture. That's the QPI, and that's what all modern servers have, memory directly accessed from the CPU. You're thinking, I'm a developer on this conversation. Why you give me a history on servers? Why do you care? Because we can't blame the server anymore. When I was first started as a developer and first started using database technology, literally the fast servers simply, they were huge refrigerators from Sun, but they simply couldn't do the workload that we wanted them to do, no matter how efficiently we coded. We don't get that anymore. Nowadays, the servers are so much faster that you really can't blame them anymore. If you can't get the level of performance that servers can give you, then it's really our fault. And just to give you an example of how insane databases can run on even modest hardware, let me do a little demonstration for you. Hopefully that font's large enough. I'm running this literally on this 4-year-old laptop. So it's a laptop machine, it's 4 years old. I'm running Oracle, but this could be any database. I'm not trying to be biased here. You could run Postgres, MySQL, doesn't really matter. All I'm going to do, I'm running on this 4-year-old laptop. This laptop cost me $1,000 Australian, which is almost nothing. And what it's going to do is there's a little bit of Oracle code here, which the specifics don't really matter. What I'm going to do is 40,000 primary key lookups. So the most simple form of database operation you can do, I'm looking up an entry in a table. I'm looking up a single person or a single customer, just primary key lookups. These are the kind of things that databases do all the time. What I'm going to do is I'm going to use Windows here to start off 10 concurrent versions of this. So 10 times 40,000 queries. And we'll see how fast this 4-year-old 1,000 level laptop can do this. Now, when I launch that, they're probably all going to launch in my other window, so my other monitor. So I'll bring a couple over so you can see what's going on. It's just spiraling through 40,000 primary key lookups. I actually started 10 of them. So we can see here on each one, I'm getting around about 46,000 queries per second. So we times that by 10. And what we're saying is that on a 4-year-old laptop that cost $1,000 with only 16 gigabytes of RAM that's currently streaming video to you, I can do 460,000 queries per second. It's insane. So this blows my mind nowadays, how incredibly powerful modern hardware is, or even 4-year-old hardware. It's ridiculous. So let's face it, if you're writing applications and even modest hardware like this can get 400,000 queries or primary key lookups per second, then really almost every application should be able to run perfectly fine. But if they don't, if you can't get good database access, then you're in trouble, because we used to write applications like this, and nowadays the database is far removed from the applications. The applications talk to some other layer, which then talks to some other layer, which might talk to REST, which might talk to Hibernate, which eventually talks down to the database. But no matter what your infrastructure is or your architecture is, the database sits at the bottom, and it's always in the very middle. So if it's running badly, if you're not getting those incredibly performance demos I just saw there, then everything else just collapses around it. Database performance is critical. Now, you might be thinking, well, relational databases, maybe they have a problem in this new modern world where we have mobile phones and IoT devices, etc. Then, you start seeing all these blog posts out there saying relational databases don't scale, even though hopefully I've just demonstrated to you that, on old hardware, we can do 400,000 queries per second. It's ridiculous how well they scale. But people still say, oh, on their application, they had some problems and that's why they don't scale. That's why we need to go to some web scale environment, etc. Don't get me wrong, NoSQL and sort of niche solutions that aren't relational databases all have their place. But this is one of my favorite quotes. The reality is for 99.9% of us, we don't need those very niche specialized architectures. In fact, as I noted before, even Google, Facebook, and Uber are starting to move back to relational database or relational database variations because they're good enough. So what's holding us back? It all comes down to too much work or not being able to do work. And after that long-winded introduction, let's get onto the SQL thing now. SQL is pretty much like any language. What do you do with any language, whether it's Java, C, C#, etc.? You compile it. The only difference with SQL is you compile it on the fly. You present it to the database and it's compiled right there and then. It's not compiled in advance. Then you run it, obviously, and then you do something with the results. So SQL is really just like any other language. Compile it, execute it, and then do something with its outputs. So if you want to have successful applications on a relational database, you obviously need to be able to compile your SQL quickly because it's done on the fly. You need to be able to run it quickly, obviously, and obviously get those results or store those results as quickly as possible. If you can do those three things, you're going to be successful. That's really all we have to worry about. Now, what everyone talks about, if you go to any conference which involves a SQL talk, this is probably the thing that everyone talks about. They don't talk about the compilation phase. They don't talk about the storing and the fetching. They all talk about the execution phase, SQL tuning. There are hundreds of books out there about tuning SQL. So this session, we're not going to go near that. We're just going to talk about the other two things, the things that no one talks about. How do you compile SQL quickly? Do we have any control over that even? And how do we store and fetch results quickly? Because ultimately, if we can get those two things right, then we got a very good chance of having successful applications. So let's go to part one, compiling SQL fast. Now we need a bit of terminology here that I can use throughout the rest of this talk. I want to talk about a thing called cursors. And if we look at some of these SQL statements there on the screen, we've got a delete at the top, a drop table, a couple of select statements, some MySQL, some Postgres, etc. The question is, which of those particular commands would you classify as a cursor? And maybe surprising to know that from a database perspective, we consider all of them to be cursors. From a programming perspective, we often think of just a query as being a cursor, or anything that we iterate through being a cursor, and everything else being, we might call it DML or DDL, etc. But from the database's perspective, everything that gets thrown at the database is in fact a cursor. Because from the database perspective, a cursor really is just a pointer to memory. And so the three phases of a cursor are open, process, close. We may think of it as developers as open, fetch, and close, but it's not that from a database point of view. The database says open, which simply means I need some memory. The client says I need to allocate some memory on the database server such that I can do some work. Once that's done, you can do some stuff with that memory. You might modify some memory, etc. You might ask for more memory, etc. And then finally, closing a cursor from a database point of view is you saying as a client, here's your memory back. It can be used for other purposes. It's very, very simple. But here's the thing. Databases are designed to serve multiple users. That's the very reason why they exist. If we didn't have multiple users, we could simply do Excel spreadsheets on our own computers. If you have multiple people accessing memory, it needs to be controlled. Now, a quick primer on database memory. Almost every database technology out there, MySQL, Postgres, SQL Server, Oracle, the others, when they come to managing their memory, almost exclusively it's done with doubly linked lists. It's just the most common example they have, because generally people have to have entry points into memory and then they traverse along these lists to find information. They might use hashing algorithms, etc., to find the entry points, But generally, once they're in the database memory architecture, it's walking along doubly linked lists. Now, let me come up with a metaphor for how we control access to memory in a database. Do you remember 2 years ago, before COVID, when we used to do things with other people? Wasn't that a lovely time? We used to go to concerts, we used to go to bars and pubs and stuff like that. And going to concerts was fantastic. The only thing that was a real nightmare when it came to going to concerts was this: when that moment you needed to use the public restrooms. And let's face it, the problem is this is a difficult thing. You're stuck in a queue. It's always hard to get to. And you can think of a restroom when it comes to database memory as a complicated structure. It's a complicated structure, a public restroom. And one of the issues with a public restroom is concurrent access to it generally is not a comfortable situation. It's generally not a desirable thing to have multiple people accessing the same resource at the same time. Now, how did we solve this problem with public restrooms? Well, it's the same as we solved it with memory. A public restroom is a limited resource. Lots of people want access to it at the same time. As we saw, concurrent access is generally not preferred, and it masks a complex system. The restroom solution was simple. We introduced a very simple locking or lightweight structure that sits in front of the restroom to let everybody know what's going on. And it's the exact same with database memory control. When people want to access the complicated database memory structure, we control it with a thing called a latch, just like we would in terms of a public restroom. We have a lock or a latch. We have the same thing. Depending on which database you're using, they're called latches, they could be called mutexes, they could be called spin locks, etc. But the way you access memory is step one is you have to acquire the latch first, just like you would in a public restroom. Once you've got the latch, then you're allowed to access the memory. That's step two. You're allowed to now access the complicated resource. The fact that you have the latch means you get exclusive access to it. And then when you're finished, you release the latch and it unlock and someone else gets to go for it. So if you're ever struggling with database memory architecture, just remember it's like a toilet and you'll be fine. So memory contention means someone has to wait. Contention for memory is a big deal because while one person is accessing memory, other people are prohibited from doing so, because you can imagine if someone changes those linked lists, then you could easily get a memory corruption. The key thing here is it's an active wait. And we have this term, what we call spinning. This is why they're called a spin lock in some platforms. It's not as if we go and say, okay, can I get the memory? Oh, I can't. Let me just wait for a while. That's actually way too long from a CPU perspective. CPUs are so fast nowadays that actually going to sleep and coming back and trying again is an eternity. So what we do is rather than giving up the CPU, if I try get a latch and can't get it, I simply try again. I literally do what we call spinning. I'm literally going, can I get the lock? Can I get the lock? Can I access the latch? Can I access the latch? Generally thousands and thousands of times before we then give up. And then we'll go to sleep for a while. And that typically is maybe 1/100 of a second, a tiny amount of time. But in the CPU perspective nowadays, where we talk gigahertz, that's a huge amount of time. So we don't sleep. We generally just do this kind of business. What does that mean? It means your server is always burning a lot of CPU. What is CPU? Let's not beat around the bush. CPU is money. Whether you're paying for a machine on premises, that means you're probably licensing it if you're using a commercial database. But even if you're not, if you're using something on cloud, whether you're using AWS, Oracle Cloud, Google Cloud, whatever, you pay generally for CPU cycles. You pay a little bit for storage and network, but most of your money is on CPU cycles. So if you're burning CPU, you're burning money as well. So memory contention hurts the CPU because people are spinning trying to get access to it. It hurts concurrency because if someone has memory, no other people can get it. And the key thing is you really get nothing done. You're burning money and achieving little. That's a key thing. Hopefully now you're going, hold on a second. I signed up for a SQL talk. And, weren't we going to be talking about SQL here? So let's bring this back to SQL now. To run a SQL statement, what do you have to do? This is what the database does when you throw a SQL statement at the database kernel. It goes through normally between 5 and 6 phases. The first phase is what we call a syntax check. The syntax check is, would this SQL statement run on any platform? And you can see there I spelt the word from incorrectly. So it doesn't matter what database vendor, what database platform, what database version, you will never be able to run that SQL statement anywhere. That's a syntax check. If the syntax is fine, we then do what we call a validity check or a semantic check. And that is, yes, this is a valid piece of SQL in terms of its syntax, but it might not run on this database. In this particular example, I spelt the employee number column incorrectly. But this could be a valid SQL on some other database if that was a valid column name. So that's the difference between syntax and semantics or validity. This is a valid piece of SQL from syntax point of view, but it won't run on this particular database. Assuming it passes those two things, then we go through what's called the optimization phase. The database makes a decision about how to best run your SQL using various heuristics and statistics that it knows about the tables involved in the SQL statement. That optimization then gets converted to what we call row sourcing. And really that's just the conversion between this nice, easy to read English version of the plan or the execution statements to a binary format, literally the list of instructions that will be executed by the database core to actually succeed and run your SQL statement. After all of that, now we can run it. This is where we actually start reading information either from memory or disk to actually satisfy your SQL statement. And if it happened to be a select statement, then we have this 6th step, which is fetching the data and bringing it back to you. So that's a lot of preliminaries. A lot of stuff happens before we actually do real work for you as a developer in terms of running your SQL statement. We call it parsing. It's the compilation phase. And all of that means lots and lots of memory access. And lots of memory access means lots of contention or possible contention and lots of CPU, because we saw before, all memory access needs to be protected. Now, you might be thinking that's impossible to avoid. I mean, I have to obviously check if a SQL statement can be run. But there are two mechanisms that many database platforms out there have to actually hopefully reduce this cost. The first one is most database platforms have some semblance of what we call a cursor cache, which is every time you throw a SQL statement at me, at the database, while we do all those steps first, we compile it, and then we remember that information such that we don't have to do it again. We keep a record of previously executed statements. So I might parse this, for example, select star from employee or employee equals 1, 2, 3. If it's already in the cache, then someone else has run this before me, which means I know now by definition that syntactically it must be valid, semantically it must be valid, because if someone else has successfully run it, then it must be correct. I can already reuse the optimization phase. So if I've worked out the best way to run this query is with a particular index, I can reuse that information and reuse the binary information that maps out the execution plan. So as long as someone else has run it first and paid that price of compiling or parsing the SQL, hopefully I can see some benefit by reusing that information. It's the database's version of code reuse. So here's a random set of 11 SQL statements, and here's my cursor cache. And if we work our way through them, we can see every time we manage to reuse the same SQL statement, you can see, for example, like this first one here, had to go into the cache, we had to parse it and compile it. But when I saw it again later on, I could bypass the parsing stage and just jump to the cache and reuse it again. So I managed to avoid what we call 2 full compilations. So out of 11 statements, I managed to get some benefit here by only not having to parse 2 of them. You might be thinking the probability of reuse is actually fairly low, given the variety of SQL statements that come into a database. 2 examples here. There is obviously no way that first statement can in any way benefit the second statement. But in reality, a lot of queries and applications are nearly the same. Someone might run a query like this, select surname, first name, where employee number equals 1, 2, 3. And someone else comes along and says, select surname, first name, where employee number equals 4, 5, 6. Those 2 queries are almost identical, except we're just looking for a different particular employee number. But we can imagine that the execution path is going to be the same, the syntax is the same, the semantics is the same, everything about them is the same, except we're just looking up a different row. That leads on to our second optimization, which is the concept of host variables or bind variables, depending on what platform you're using. And that is, what if we can parse a SQL statement, but not use a particular literal value? I'm telling the database, parse this particular SQL statement for a representative value. We don't know what it is yet, but I'm just saying, assume there's going to be some value there, just parse that. That goes into our cursor cache, and then we can now reuse that for multiple different executions. So I can rerun that statement multiple times, each time finding the same one in the cache, even though I'm using it for different values of the employee number. If I repeat those same 11 statements, now that I'm using placeholders or bind variables, we can see the likelihood of reuse jumps up considerably. I've gone from 2 avoidances of a full compilation to 5 full avoidances. So this is a good thing to have. Let's do a demo now to see if this is actually worth our time. I've got 2 very simple Java programs here, and this is a snippet from each one. The first one will use simple string concatenation. Therefore, every single one of these commands, every single one of these SQL statements will be different. The first one will be primary key equals 1. I'm going from 1 to 10,000. Primary key equals 2. This will be 10,000 different SQL statements. This one here, this second program, is the exact same amount of work being done. We're doing 10,000 SQL statements, but I'm using this placeholder now. And what will happen is this will be parsed once, and then I'll get to reuse that information 10,000 times. Let's see what the difference is between these 2 things. So let's bring up a window. Hopefully people can see that. So parse demo will be 10,000 different SQL statements. Each one has to be parsed and compiled by the database. We'll see how it runs. You can hear the fan on my laptop going off. Okay, so we did 10,000 different SQL statements, and we managed to do them in what, 9,000 or almost 10,000 milliseconds, so 10 seconds. So we averaged about 1,000 parses per second. Let's now do the exact same amount of work. I can't stress this is important. This is the exact same executions, 10,000 queries. This time we only have to parse the first one. And we're done. So we can see we've gone from 1,000 executions per second to nearly 10,000 executions per second. It's 10 times faster when we manage to avoid that parsing overhead. Let's go back to our slides. When I used to do this talk 5, 6, 10 years ago, when servers were slower, people would go, wow, that's so impressive. But nowadays, they don't do that because people say performance looks fine to me anyway. I've gone from 1,000 executions per second to 10,000 per second, but 1,000 per second is great. I mean, let's face it, very few applications need to do 1,000 queries per second anyway. So performance still looks fine. It does look fine because that was a really trivial query. Let's make it real. As developers, either we write more complicated SQLs, or if we're using things like an ORM, then the ORM generally generates far more complicated SQL statements. So let's now repeat that demo with a slightly more complicated SQL. Now I've got a join between 2 objects here. These 2 objects in themselves are database views, so they in turn hold complicated SQL behind the scenes. These are the kind of things we genuinely write as developers, or the ORM writes for us. We write complicated SQL statements that the database has to fulfill. Let's now repeat that parsing demo with more complicated SQL statements, and presumably the database has to work harder to compile those SQLs. Now in this one, it actually takes, I'm passing in an argument, this is the number of executions I'm going to do. Now I want to stress here, I'm not actually running these SQL statements. All I'm doing is compiling them. So I'm not actually even running the query. I'm just telling the database, find out if this query is valid and what's the best way to run it. I'm just going to do 10 of them. This gives you probably a more realistic view of what the cost of compiling SQL is. I only got 4 queries per second, not 1,000. And it doesn't get any better if I dump it up. Let's try 20 of these queries now. That doesn't scale because there's a certain amount of work that must be done no matter what. You can see it's still 4 per second. We can't do any better than that on this old laptop because of the amount of work that a database is doing to work out how to run this query. What if I now use a placeholder? So I only have to parse it once, and then I get to reuse that information in the cursor cache. What does it cost now to do 20? 74 per second. And that's only because I'm actually getting, it's so fast, I'm actually getting the thing finished because I did 20. If let's try 2000. Yep, even that is sub-second. Let's try 20,000. Now it's taking a bit longer. This is perhaps a much more realistic view of the benefits of reusing information from the SQL statements in the cursor cache. We've gone from 4 queries per second when the queries are complicated to 4,000 queries per second. This is a 1,000 times performance benefit once you start getting into real-life application queries. Hopefully that convinces you that reusing cursor information is vital to successful applications with any database. If you don't care about performance, maybe even 4 queries per second is good enough for your application. That strikes me as weird, but if it is, let's forget about performance. Even if performance was the same, there is something much more serious when it comes to not using the cursor cache efficiently. The most common reason we have parsing issues or compilation issues where every SQL statement looks different is because we're building SQL statements like this. When you start building SQL by concatenation of values, such as we have here, such that we have literal values floating around in your SQL statements, you will get hacked. Simple as that. Here is the problem when you take input from an outside influence, like a user or anything else, and pump it directly into a SQL statement. Here is my query. I'm expecting someone to pass in an employee number. So this is what I was expecting. I'm going to run this query, and I was expecting someone to provide me the value of 6543. Someone malicious might pass in this as a value, 6543 and 1 equals 0, which means that top half of the query will return nothing. Union all, select table name from all tables or data dictionary or information schema, depending on what database version you're using. This person is now looking for tables that have the word security in them. Let's say they find one that might come back to their screen as an employee name, and then they'd go hunting in that table, app security, looking for things like usernames. They are building up SQL strings, passing them in as input in order to hack your system. Here's the problem with hacking. We've seen all those movies where hackers are these, people that sit in dark rooms with hoodies on, and they've got incredibly vast computing power, and they live in strange countries in special places, and they speak in foreign languages, and they're very, very sophisticated. And we would think, why would they ever have any need to hack our small system over here? Even like people like Donald Trump. In fact, I'm not sure if I'm sharing my sound at the same time, so let me. I might just have to point my microphone. Let me play this.
To get hacked, you need somebody with 197 IQ, and he needs about 15% of your password, right?
Hopefully you all heard that. So even dignitaries like this don't really have a firm understanding of how easy it is to get hacked, because no, they don't need your password. They don't need a genius level IQ. You'll get hacked super easily if you allow SQL statements to be built by concatenation. If you're wondering what incredibly sophisticated tools those hackers out there are using, the #1 hacking app on the planet is Google. Simple as that. Now, I'm not sure what the rules are overseas in terms of hacking a website. I know here in Australia, it's very much illegal. You can go to prison for that kind of stuff. So I'm not going to hack a website live on this call. That would be not smart for me to do. So what I did was I videoed it, and we'll play the video. Hopefully this will keep me away from any law enforcement authorities. We've done some protections here to make sure no one gets harmed. But literally, this is how you hack a website. It is this easy. First of all, I'm going to looking for any websites that are using PHP. That's the most common. Yeah, they're using, say, LampStack or something, and they've got an ID number in their query. So I found one. Anyone that comes back in this result said it's probably hackable. I found one here. I'm not going to show the URL. I go to their website and I simply go to the URL, and where it had PHP equals some number, I'm going to replace it with a quote. And I hit return. If that crashes the site like it did here, I pretty much can guarantee they're building SQL statements up by concatenation, because they were expecting a numeric input. Putting in a single quote when you put that into a SQL statement results in an invalid SQL statement, and I have an error in my SQL syntax. Literally, that 30-second exercise tells me this site can be hacked with SQL injection. And the only tool I used was Google. Now that I know that, I could simply go to that site and start adding special edits into the URL in order to hack that website. And what I'm doing is, that's obviously an incredibly small font. If I zoom in, what I'm really doing is starting to build those kind of SQL statements we saw before that I explained with the employee table. In the URL, I'm building up a SQL statement that looks something like this to go hunting through this application tables that I'm not meant to see. Now, you might be thinking that's obviously going to take a lot of expertise on my part to very carefully build up those URLs in order to go data mining to try and find out weaknesses and exploits in their application. But of course, it's way, way easier than that. There are free tools out there on the internet that will do all of that for you. Here's one called Havij. It's literally an advanced SQL injection tool. All you do is you put the URL of this site that you've worked out that you can hack along the top and press go. And the first thing it does is it goes and finds out what particular database it is and finds out where the data dictionary and the databases are. Once it's done that, you can see it's finding out the number of dictionaries there. Once it's found that, it then says, okay, I'll go find the tables for those particular databases you've nominated. And it goes down and finds the tables, finds a list. I can pick which ones I'm interested in, and then click on get the columns. Once I've picked them, there's one here called admin user, admin, etc. That looks like it might be security. I can go pick on some columns and see if I want to get some interesting columns out of there. And once I've done that, I found some columns, or password, email, they could be useful. I simply click on get data and it starts finding the information. Every single one of these things you've just seen are done by sending a very complex URL over to the website and building up a SQL injection string to find out the information. So literally with Google and a free software tool, we're into that system. It literally is that easy. That's what it takes nowadays. It takes 5 minutes to hack any website that builds SQL by concatenation. If you want a really good blog post on that, Troy Hunt's a security researcher here in Australia. He's got a good blog post that hacking is child's play nowadays. For example, these two people, they're just like a couple of 12-year-old kids. They hacked almost the entire school district in a particular state in America, really just for fun. They weren't doing anything nasty. They're just doing it for fun to see if it can be done. It's amazing. So hacking now is so easy if you're vulnerable to SQL injection. This really happens still today. People often think that SQL injection is a solved problem, but it's not. This is Stack Overflow just the other day. I was on there actually doing you can see here, it's an Oracle error they were having. And so I was trying to help them with an Oracle problem. And then I saw this. So you can see they're building up their SQL statement just by concatenating the values in. It still exists today. And in fact, there's lots of articles out there on the web. So you've got, free pick data breach, SQL injection. WooCommerce, SQL injection vulnerabilities. The Stanford Daily, hacked with SQL injection. SQL injection probably still is the #1 hacking mechanism, and it comes from building by SQL by concatenation. You might be thinking, phew, luckily we don't write our own SQL. We use an ORM, so we're safe. But don't forget, an ORM is just a SQL application that someone else wrote. And so even ORMs can be vulnerable to SQL injection. As developers, we have the responsibility, whether they're writing SQL or whether we're asking an ORM to write an SQL, to continually validate that it's not passing vulnerabilities of our applications out to the outside world. How are we going for time? Just checking my time here. So if you want fast, secure SQL, always bind or use these placeholders, especially if it's coming from user input. We saw the speed benefits there, up to 1,000 times faster, and more importantly, the security benefits. Whilst we're talking about binding, reusing information from the cursor cache, I said before that if we have something that's using a bind variable or a placeholder, if we parse it, It's already in the cache. Fantastic. We get to reuse. We know by definition now that it's syntactically correct, semantically correct. So all these things, we've ticked the boxes. It doesn't necessarily guarantee that we can go ahead and use all the other information we've stored about that SQL statement. You might be thinking, how? Why might not we be able to do that? We might have some parsing still to do, even if that information is in the cache. And this is the definition of what we call the difference between what we call a hard parse, which is doing all the steps, and a soft parse, where we found a SQL statement in the cache, but we could not use all this other information. Let me explain why that might be the case. A user Scott might log into the database and run this query. Then a user named Mike might also log into the database and run the exact same query. This would be found in the cursor cache. This person would find this exact query already in the cursor cache because Scott has run it. Most of the time, you would imagine that he should be able to reuse all the information that Scott has stored. The one time it might not be the case is if Mike has his own copy of the employee table. These two queries have the exact same syntax, but they might actually be pointing to different versions of the employee table. In that case, you can't reuse all the optimizer information, etc., because you're pointing at two different tables. This is what we call a soft parse. Soft parsing is not as expensive as hard parsing because we're not doing all the steps, but it still requires memory access, which means spin locks, latching, and therefore burning excessive CPU. And the question is, can we do better? Can we even do better? So let's recall what I spoke about cursors. Cursors are open up some memory, use that memory, give the memory back. So in our cursor cache, here is our SQL statement with all the information about that it's correct, the optimizer information, the execution plan, etc. It's sitting there waiting to be used. And the first person that used it opens up a cursor to it. And while that cursor is pointing to it, they get to reuse that information and run a query. They get to run a cursor against it. But when they close that cursor, when they've finished their query, they lose that pointer, which means the next time they run that query, they have to go double check that entry in the cache to make sure it's still appropriate for them, which means the next time we run that query, we have to do this thing called a soft parse. Just that double check to make sure that that information in the cache is valid for us to reuse. This is what you see if we turn on what's called a database trace. This is an Oracle database trace. Other platforms have similar facilities. I've run this statement 10,000 times, and I had to actually parse it 10,000 times, even though it's the same statement and it's using a placeholder. The first parse will be an expensive one. It's called a hard parse, a full compilation. The other 9,999 will be soft parses. We actually went in there and said, let's check if you're actually valid for me to reuse. Yes, you are. Okay, I'm fine. It was still a parse, but a much more lightweight one. But it still costs you. Those 10,000 parses added up to a net total of 0.4 of a second of CPU time to actually do those 10,000 executions. That sounds impossible to avoid, but what if we don't close the cursor? Here are some cursors that I've got that I've run. I've run select star from emp, select star from department, select star from employee. I've got 3 cursors I've used in my application. This is how I would normally, prepare one of them. This tells me the database to parse this and put it into the cursor cache. What if I could do it this way? What if I said, if it's the first time I'm running this particular query, then I'll parse it. Otherwise, rather than doing a reparse, I'll simply reset the cursor pointer, say, throw away my results, reset the pointer back to the start of the cursor, and re-execute. I only ever parse it the first time I see this query. My application would be responsible for this. It needs to remember what queries I've run and then decide whether it's the first time or not. So in a nutshell, what we're saying is we never close cursors in our applications. We don't close the cursor. Therefore, we're holding onto that pointer in memory to the cursor cache. What that means is the application now needs to remember a list of every distinct SQL statement it's ever parsed and then reuse them whenever possible. Now, obviously, if we have hundreds of thousands of different SQLs, we can't hold on to all of them. We'd run out of memory. We need to decide some way of throwing away the oldest ones. And obviously, if someone drops a table our cursor pointer, which points to that information, needs to be thrown away because that SQL statement is no longer valid because someone else dropped the table. Now that sounds pretty complicated to write all of that in the application tier itself, which is why a lot of people don't do it. But luckily, that work has been done for you by the lovely people who write drivers. So for example, this is the Oracle driver. Most other drivers do the same thing. If you set a few properties, namely, I want to do implicit caching, and I've said I want to hold up to 50 statements, we will keep cursor pointers open to statements in the cursor cache, even if you close it. So doing this kind of stuff then gives you information like this. I ran this statement 10,000 times. The actual code you write said, prepare that statement or parse that statement 10,000 times, but the cursor caching said I can avoid that. I only had to parse it once, and we can see we get a significant drop in CPU. This is optimal. The ideal for an application is to parse each unique SQL statement only once for the lifetime of the application's lifetime. That's perfection. As I said earlier at the start, I have one slide which has an advertisement in here, which is PL/SQL, which is the Oracle Stored Procedure Language, does all of that for you with no extra work. Any SQL statement inside PL/SQL automatically uses bind variables and automatically holds cursors open even if you close them. In PL/SQL, if you write code that says open, fetch, close, the database goes, you know, you don't really know what you're talking about. I'll just ignore your close command and reset the pointer. So if you put your code into PL/SQL units in the Oracle database, you get optimal execution always. That's my one little advertisement for this talk. That's part one finished. Thankfully, that is almost the vast majority of this talk. If you can get not getting hacked and making sure you lower the parse counts to as low as possible, you're well on the way to optimal database performance. We're going to finish off now. We got 10 minutes left. Finish off now with getting and storing the results and how we do it fast. All application vendors use the same thing. We have platforms out there and they read and write to the database. And when we start with reading data, it's a very simple mechanism. When we're querying data, we don't actually read rows from the database. We read blocks or pages. They're simply different names for the same thing. To read data from the database, you actually read blocks. And this is what almost every database does because disks used to be slow. We read from disk into memory, and then memory gets passed on to your application program. But remember we said reading information from memory is complex because at all times, there's lots of stuff going on. People are querying from the employee table. People are changing the employee table. Other queries are going on. People are adding new rows. There's lots of versions of the same data floating around in memory at the same time, which means we have to use latching to control memory access, even when we're just reading data out of memory. To fetch a row from a table, this is what normally happens. We get a latch to protect a block in memory. We find that list of blocks. That latch protects multiple blocks. We read the block. We find the row from that particular block. Then we release the latch and give the row back to the client. When we fetch, we loop through a cursor. We do the same thing, but lots of latching. It's a typical program that does this. Execute query, fetch, fetch, fetch in a loop, does the following. Get the latch, walk along the list of blocks, get the block, get the first row, release the latch, give the row back. Get the latch again, walk along the list of blocks, probably get the same block again, get the next row, release the latch, give the row back. Third row, get the latch, find the block, get the row, release the latch, give the row back. Lots and lots of latching just to walk through a list of blocks. A better strategy that most database platforms implement is a thing called pinning. To fetch a row, pinning is the way you tell the database, look, I'm not just getting one row, I'm probably going to get lots of rows. I'm getting all the sales for this year. I'm getting all the customers with a promotion. So you're telling the database, I'm probably going to need lots of rows from each block. If you can tell the database that, the database knows. It says, I'll get the latch, walk along the list of blocks, find the block I want, and put a pin in it. A little marker saying, Connor's interested in this block for a while. Now I can release the latch because my pin is there saying, no one please touch this block. Now I can examine that block for lots of rows. All the rows that match my query criteria in that block can all be extracted at the same time. Then I get the latch again, find my block, take away my pin, and release the latch. So how do you say I want lots of rows? How do you say to the database, by the way, I'm probably going to need lots of rows? The database doesn't know in advance, so it's a responsibility of the client. Now, it's telling me here to start my demo early because it takes a while to run this one. So let's start that running and come back to the slides. But this is how we do it. Here's a typical Java program. I'm going to do a query that loops around lots and lots of rows. I'm going to do the normal code, just fetch a row at a time, fetch a row at a time. But the way I tell the database I want to use pinning is with this. I use a thing called set fetch size, and I'm passing it in from the command line in our demo here. So if we go to our demo, which I've now left running for a while, I said use a fetch size of 2, which in Oracle is the smallest fetch size you can use. You can't actually fetch one row at a time in Oracle because we always fetch the second row to see if we've finished the cursor. To query 500,000 rows took 15 seconds. That's why I started it beforehand. And we got about 30,000 rows per second, which still seems good. But what if I tell the database, I want 200 rows at a time? The database knows it'll be pinning now to get multiple batches of rows at once. Let's see the difference. Now I'm getting that done at what? 900,000 rows per second. Let's bump it up to 2,000. This is insane. Once again, 4-year-old laptop, old technology. This database can query over 1 million rows per second just by telling the database that I want to use pinning, get batches of rows rather than one row at a time. So we really want to focus on blocks here. That's the key thing, right? We're not worrying about getting rows at a time. We're telling the database, go get blocks of data at a time because it's much more efficient. Also, if this was done across a network, which this isn't, this is all running locally on my own machine here, we get benefits because we're reducing the number of round trips to the database as well. Now, there's no such thing as a free lunch. I'm just conscious of time here. We might go just a couple of minutes over if that's okay, Rita. There's no such thing as a free lunch because all that data has to go somewhere. If I'm going fetching 1,000 rows at a time, they're all coming back to my Java program. They're all coming back and have to be held in memory. Let me give an example where that becomes a drama. So I'm calling this one Java Fetch Demo Hold because what this one is doing is it's fetching the rows, but when it's almost finished executing the cursor, it's going to sit there and sleep for a while so I can go dump the Java heap from that running program. And you can see here, it's used about 4 megabytes of memory. That's nothing because I'm only fetching 10 rows at a time. If I'm unhappy with that performance, I say, look, I'm going to fetch 400,000 rows at a time. It's going to be a lot quicker. Don't get me wrong. It's going to be, let's create the table. Let it get off. It's going and fetching now. So it's going to be much, much faster. But it used 350 megabytes of memory because it dragged 400,000 rows back to the client. I don't care how big your server is, right? If you've got a couple of hundred Java sessions in a connection pool, each using 400 megabytes of memory, then that's a bit of a problem. So you don't want to be doing that much. Generally, there's a sweet spot. If you can fetch maybe a couple of thousand rows at a time, you might use 10, 20 megabytes of memory, and you'll get almost the same levels of performance. Because ultimately, we're looking at rows on a block, and a block only holds 8K worth of rows anyway. So our final little bit here, just the thing about the opposite direction now. We've read data really fast. Let's store it really fast. And the same rules apply. If you're storing one row, if you need to store one row, fine. If you need to store lots of rows, think in terms of storing them in batches and not rows at a time. So our final demo is to show the insert performance benefits when we have batching if required. Insert, let's get the T right. So this one is, how fast can I insert rows when I have lots of rows to store, one row at a time? I can do 10,000 rows in about 3 seconds. But if I do them in batches, I think I've hard-coded batches of 1,000 here. Those same 10,000 rows can actually be inserted in less than a second. In fact, let's try 100,000 rows. Also less than a second. Let's try 1 million rows. even that. I've gone from 3 seconds for 10,000 rows to over 1 million rows per second, once again on a 4-year-old laptop. If you tell the database what you need to achieve, in this case, I want to install lots of rows and code appropriately, you get these incredible performance numbers. So let's summarize that. We're pretty much out of time. If you want slow, insecure applications, don't use any binding, don't use any SQL reuse in the cursor cache, don't use any pinning of large-scale rows for blocks. You'll guarantee your applications are slow, terrible, and hacked. So if you want fast, secure SQL, hopefully I've proven to you, and therefore fast, secure applications, if you bind or use placeholders for your user input, that gives you a cursor cache benefit. If you use pinning and array processing, that lets you drag rows out of the database and get them in incredible performance numbers, as you saw here today. Can you imagine what you could do on a genuine server as opposed to a laptop? And most importantly, all that stuff will stop you from getting hacked as well. My fun little pros here, if you're using Oracle, think about using PL SQL because it takes care of all of that for you. I'll finish up by saying Merry Christmas. I probably won't see you before the Christmas, so Merry Christmas. Have a fantastic holiday. Once again, if you want to stay in touch, please follow me on Twitter, or you can hit me on my blog or my YouTube channel. Thank you once again to XGeeks for having me. I'll try to say that, let's pronounce that correct. XGeeks for having me. It was lovely to be invited. Thank you, Rita, and hopefully you all had some enjoyment out of this session and learned some cool stuff about database technology. Thanks, Rita.
Sweet. Thank you so much, Connor. We sure did. Even myself, which I'm not technical, I was quite excited to hear your feedback. So thank you so much for that. It was awesome having you here. I hope everyone enjoyed as much as I did. So thank you once again, Connor, for your availability, your insights, and also for leaving this open door for us to get in touch with you in the future in case we have questions or would like to discuss other insights on this. So thank you so much for that. For all of you over there at home watching us once again, thank you so much. We actually have very good feedback from João Henriques here, saying it was a very good talk, so good. Thank you so much, João, for your feedback. And Connor, props to you. Thank you so much for making this happen. And once again, we wish you I'll make Connor's words mine as well. So we wish you all a great Christmas. It's actually the last live stream that we're going to have during 2021. So we'll see you again in 2022 for a new series of events. But meanwhile, you can not only rewatch this great talk, but also the ones that we've done previously. So thank you so much once again, Connor, and to everyone over there at home. It was nice to have you, and have a great rest of your week. Bye, everyone.
Thank you.